So we spent a lot of time building an engine which described stations and sensors and triggers that would change behavior and so on. We made designer skins so that you could describe, here's the stuff, and by the way, it'll be this model, it'll be this manufacturer. Stored in a database so it's scalable. Instead of just on your desktop, it's now a system with several designers scattered across the province working on a provincial monitoring system. And then with operations, where each of these are speaking completely different languages. But as it comes in, the operator says, oh, it's on this port, I know it's this kind of station, it speaks this language. I can now turn it into a general message. This is data. This is a status change. And then we can process it through. We can send it out to various measurement databases, including standardized enterprise kind of things. And we can start doing things like trigger management. This behavior happened. We see this out here, we want to change our sampling. These, unfortunately, are horribly old shots of our system. But the idea is that with this configuration stuff, it's going into a database, which can be accessed by several different programs operating on the network. Okay. And we've got, the next step is to put it in a GIS view. Again, a different skin. You double click on this guy, you get that property panel and you adjust it. Depending what hardware you set it is, it can then send the configuration out and it can update your database, which may in fact be exactly the same GIS environment in which you're looking. You now have data in context, which is pretty powerful. We're now starting to design here. The other thing we've got with that trigger mechanism is we're starting to say, well, most of the time it's boring here. I don't want to fill my water quality samplers until it starts raining. So you've got these dumb little sensors out here that say, hey, it's raining. I recognize it's raining. I've set up rules to say, hey, you need to change your sampling rate. These are completely different vendors working on different radio modems, have no idea how to talk. They don't even know there's an idea of collaboration. They're just dumb pieces of equipment. Suddenly it's acting in a coordinated fashion within the network. This is very powerful. If you can do it in the field, do it in the field. It's cheaper to process there than to communicate directions and stuff back and forth. Again, with our system, we plug in a component to describe how this station's configured, how it talks, what its capabilities are, let it do the job. We configure it as such. If not, we'll just say, hey, give us data, we'll watch and see what's going on. Now you have interoperability for hardware that wasn't built to be interoperable. Just a couple of other notions we can build on now that we've got this core is the idea we can now get more data, but do we have better data? Because again, think about what a sensor gives us. We think it gives us data, which we do a little interpretation, we've got information. It doesn't give us data, it gives us numbers. There's nothing in between numbers and information. That's what we got. We need context. So we need a number to have context to give it meaning. That turns into information. We need to describe that context, which is something called ontology. We use in computer science, sounds artificial intelligence and all that. It can be. That textbook you read about watershed hydrology, environmental science, business transactions, that's an ontology. It says what's important in the world and how they relate to each other and what they mean. That's an ontology. We just need a way of capturing it. I'm going to skip over this. Once we have a method of telling the computer what the context is, what this ontology is, it can start turning the numbers into information and reason on it. So we built a thing called reason. We tied a GIS to an expert system so that it could do GIS operations, gather data, and so on, but it could also apply rules to decide what's going on. We set up a way to bind to data sources, including the types of things we got from Profusion, sensor observation services, and we put in a way to describe the way the world works. So for example, we could describe a hill slope. We could describe shear zones and different block materials and the working blocks that result from that. The idea of wells and piezometers and the boreholes with inclinometers. We could then apply reasoning that if you have water levels, you also have a water table, which you can figure out. We can then describe what's important. Inclinometers jiggle all the time. It's when they jiggle too much, and too many of them are jiggling, and they're all in one little piece of rock. That's a problem. When the water table's getting up close to lubricate that shear zone, that's a worse problem. So we describe a nice little workflow. Suddenly, now the system's saying, instead of showing us graphs, it's saying, according to the way you think the world works, here's something important. This is bad. Go look. Decision making is still in the human being. That's what we're good at. This is just doing the mechanical work for us. So we need a way, of course, to get the data into this system. We've now got a way of taking numbers from anywhere out there and turning it into data at least. But we need to go the next step and put it in a way that works for expert systems. So we built this engine that takes data sources, takes data description, like what the columns are and so on. The idea of a conceptual ontology, that's like us describing to somebody else how the world works, and turn it into something a computer can use and push it in. And again, we're modeling the workflow. In each case, we can change. Forget about sensor ML and OGC. Let's use a different standard. We'll plug that in. Oh, we changed what expert system we're using. That's fine. Put in a different translator. And so we can go from one system to another. More importantly, we can connect one system to another. As people have built things that are very clever doing the jobs they do, we now have a way to glue them, which is important. So now we have a way to take different kinds of sensors, put them into a common stream, and flow it into a system that can actually make decisions based on your instruction of what's important out there. Another piece is modeling. We built this simulation modeling framework so we can build landscape models and little autonomous agents, and we can put probes on them to see what's going on. And we can change what they see. So for example, we might just collect data, put records out of what's happening in the model. But this is an example where we had squirrels running around. They look at the world differently than us. So we could put perceptual filters on them as to what the state of the model now. The other thing we can do is we can, goof around with the number, kind of like the sensor doesn't quite measure right. We can now simulate sensors. So we tied this all together in Ecocosm. We built a top model-based watershed model, just something simple, just to prove the point. And we modeled we took the precision model published by these sensors, and we built sensors that act the same way these do. They don't report what's really going on, they report what sensors are going to report. And we fed it all into that same infrastructure. Simulated data is going out just like the stuff coming from the integrated modeling platform, or monitoring platform. Rainfall's real. Water levels are fake. This tool has no idea. We got this from Germany. That taps into sensor observation services. So now we can work with data that's tagged as simulated and use it with real data. Phenomenal powers here. Planning sensor deployments. It's brutal to get it done, and then you find out it doesn't work right. So it's telling me I got 1 minute. So you can actually run a landscape, put things out, see if you're getting the kind of data you would expect to get. We can simulate communication problems. So we can deal with a lot of the radio modem voodoo before we have to go out in the field where it's expensive. We can test the applications we build. Landslide, if you're building a decision support system to handle hill slopes, I'd rather not wait around until a hill slope actually slides into the reservoir before I find out the system works. I can build a simulated scenario of hill slope failures and see if the system responds correctly, all using the operational tools. And of course, we can now feed things through. Sensor observations come in. We could model different scenarios of what that data means to see what happens. So now we can kind of tie it all together using our interoperable things. We can go further steps and actually have reason set up a model to try different sampling scenarios. The world changed. I need new kinds of data. Which sampling strategy would work best for me? I'll run some simulation experiments. I'll now push it out to reconfigure the system live, because now we're working all in the same system. It doesn't matter that that sensor's stupid, as long as I can send it a configuration command, I now have a dynamic system that is changing based on what's happening in the world. What's next? Events. This is what we care about. We don't care about that graph. We care about looking at the graph and seeing the spike. That's important to us. The world changed. So how do we manage this? Event recognition, event interpretation. Shockingly, there's a standard coming out to help manage this. If we think about everything going on where you're looking for SEC violations in stock trading transactions, when you're looking at network problems with packet transfers, they're doing event-based processing. Why can't we? It's an environmental problem, but we've got lots of numbers. We want to look for bigger patterns. That's where we're going. So what am I saying? There's a gap between the different disciplines. We need to bring it together. Got to collaborate. Got to be done better. We're not going to build complete solutions. Sensor challenges are difficult. Getting partners to buy into it is very difficult to do because we have to see some value. Won't happen unless we deploy stuff. Lab testing isn't enough. We need to go out and see what happens when we actually get mud on it and see how the whole system behaves. Technology changes and lots of other clever people are building clever things that could work with the same data or could give you data. So we've got to work with interoperability. We have to make these things in a way that they can connect to other things. Even if we can't imagine what it is, it's got to be out there. Main message, environmental monitoring has nothing to do with numbers. I don't care about numbers. I care about what the numbers tell me. So we need to build these systems that let the numbers tell their story. So that's our approach to environmental monitoring using sensor webs. I hope that there's something valuable there for you as well. Every piece we've built, I expect somebody can build it better than me. We're glue. We have demonstration pieces. I want to find more partners, technology developers and users who can help build this framework. The more we build into it, the more powerful it is, the more we do with it, and the more benefit